Dear students, welcome to another lecture of electricity and magnetism. Last time we calculated electric field due to some point charges, a couple of point charges, and today we will keep on doing that kind of stuff for another configuration, that is the electric dipole. So today our aim is to study the electric field at some distance, a bit far away from that electrical dipole. So let's define first what is an electric dipole. So an electric dipole is the combination of a positive and a negative charge of equal magnitudes. There is a charge like plus q, and there should be a charge minus q, and they should be separated. So the way they interact with one another, they they constitute a dipole, electric dipole, and the field they create, we will going to see how it looks like and how it varies. So first we look at the situation as depicted in the diagram. So we have two charges of equal magnitude but of opposite sign. We have a plus q charge here given by the yellow sphere, and we have a point charge minus q given by the blue sphere, and they are separated via distance 2a. So if we want to determine how much is the dipole moment between these two charges, the dipole moment is given by a symbol p. It's a vector, and it is given by p equals charge on any one of the any one of the charges, and the magnitude of charge on any one of the charges times the distance. So it is q times p, or displacement what you call it. So dipole moment is a vector, so is the this displacement vector. So now if we want to determine the magnitude of this particular dipole given in this figure, so we will write it like p magnitude is equal to q times 2a. So this is the dipole moment of the given at any point close by. But if we are far away, like at a point p that is given here, so then we have to determine the electric field at this point p due to this dipole. Previously we calculated electric field due to two charges that do not form dipole moment. This time we are discussing uh, these two charges not as separate entities but one thing. So we will consider these two charges, although they are separated via some distance 2a, but still we are going to consider them one entity, this thing, this whole thing, and we will determine electric field due to this dipole at a distance y, at a point p at a distance y, and the distance y is such that it is much greater than this. Y is much greater than a, is much greater than the half distance between these two charges. So let's proceed. So to calculate the electric field between these two charges, we have to draw the vector diagram, and from vector diagram we will be able to determine the electric field components. So just pay attention. So let's consider initially the plus charge q. So the plus charge q is positive, so it would have an electric field pointing away from it. So this is the electric field at point p, the direction of electric field E due to charge q, and we call it E1. Since it is not pointing along any of the axes like y-axis or x-axis, this is x-axis, this is y-axis, so it is in between these two, so it would have components. So it would have a component along x-axis, and it would have another component along y-axis. So this field would have its component along x-axis given by this vector, which I'm drawing. Where I should draw somehow with the clearing. I should draw it with the blue one. So okay, so this would be the component of E1 along x-axis. So that would be E1x, and its y component would be along this axis, and it would have a direction like this, and we call this as E1y. Similarly, we would have components due to charge q minus q, but you have to see that since minus charge q it's a minus charge, so its electric field would not be pointing outwards, but it would be pointing inwards. So this is the uh, electric field due to charge q1 by given by this arrow. So again, it would have two components because it is not along any of the axes. So its x component would be again along the same direction where the x component of E1 is. So again, its x component would be in the same direction here as I have drawn, but its y-axis now, because it is pointing downwards, it would be opposite to the y component of E1. So the E2y, this is E2x, but E2y would be in the opposite direction to E2 E1y. So the thing is, when we have this kind of situation, so because the charges are equal in magnitude, since the magnitude of q positive is equal to the magnitude of q negative, so the thing is, their y components would be equal, their x component will also be equal. So I write this explicitly on the side, since magnitudes of the charges are equal, therefore their components, yeah, their component magnitudes will also be the same. So we have in the beginning q magnitude equals q negative magnitude. So we have E1x would have the same magnitude as E2x. This is the x component of the fields, and in the same way we will have E1y magnitude equals E2y magnitude, and because they are in the same direction, so their uh, magnitudes would be the same and direction would be the same, but these two E1y and E2y are pointing in opposite directions. So what will happen, that they will cancel one another. So these two cancel each other, So there will be no field. The result of this would be that there would be no field no net field along the y-axis. So total field, we call it E, that would be E1x plus E2x. That would be the net field magnitude. And since here we have seen that E1x is equal to E2x, so we can just write E1x plus E1x, so that is 2 times E1x. That would be the magnitude of the net field due to this dipole. And now we should revert back to the image, and we should determine what is E1x actually, because E1x we have written just like its symbol, but we have to determine what is it, what it should be according to the geometry. So let's go back to the geometry, and we see here that E1x or E2x, because they are both pointing in this direction, so they are actually cos of theta components. X component is cos theta. So what we say, we write here in the in actual, we write 2 times E1. E1x is E1 cos of theta, so that becomes 2 times E1 cos of theta. So that is pretty straightforward to judge. And another thing that you have to remember is that E1 is simply, if you just want to calculate E1, that is A E times charge, that is Q, and divided by, because we have to write the magnitude of charge, it doesn't matter whether it's positive or negative, because their magnitude is the same, and divided by the distance between the point P and I just write distance here, so you are not confused by what I am doing, distance squared. So now if you want to calculate a distance between any of the charge, because they both the charges q positive or q negative both have same kind of distance from this point P. So we have to determine what is this distance. So this is can be either this r or this r. Both are the same distances. This is r and this is also r. So we have to determine this r using the construction of the problem and some trigonometry, like simple trigonometry. So these are the angle theta. They are equal angles because from the central line, this point P is lying on a at the middle of a central line. So these angles are equal. These two thetas are equal. Whatever the value may be, there can be 30 or there can be 45 or there can be 50, but both these angles are equal. So they both constitute a right triangle. We can take any one of the right triangle and we can determine the cosine of theta. So cosine of theta is base over hypotenuse. So base is A in any of these right triangles. Base is of the side is A and the hypotenuse is R. And R, since we don't know what is R, so we have to write R in terms of base and the perpendicular. And we have base equal to A and perpendicular equal to Y. So we use Pythagoras theorem and we write r equals y square plus a square whole square root. So where I have written distance, so I just elaborate it. So the distance is equal to r, and r is basically by Pythagoras theorem y square plus a square square root, and we just put it back into the formula in the formula here, and because this is distance squared, so we'll have to write y square plus a square. So we from to write the value of this value of e1, we just put it back here, and we remain uh, we forget cos theta for the time being. So in a middle step we will write e equals, I write it with a different ink so that you can differentiate. So there is a step in between, so where we have 2 times e1 ke, sorry, e1, we are putting values of e1, so no, e1, so 2 times ke q over y square over a square, where we have put the value of e1 times cosine of theta, and then we have to determine what is cosine of theta actually, and cosine of theta is again so this is the value of electric field, and cosine of theta, I told you, this is square root of uh, uh, this is base over cos of theta is base over hypotenuse, and base is your base is a, and hypotenuse is again y square over a square square root. So you now in the next step you plug in the value of cos theta here, this value here, and this is the next step, and you got now 2 times ke 2 times ke times q divided by y square or a square because of this distance, and then due to cos of theta you get this thing here. So you combine, you get in the next step you combine ke times 2qa divided by y square over a square. So there is 1 power here and 1/2 power here, so this becomes y square over a square raised to the power 3/2. So now we have a final formula for our electric field due to a dipole, that is given by this guy here. And now if you go back to the definition of the dipole moment, so dipole moment we define that is given by the magnitude of dipole moment is 2 times qa or q times 2a, however you read it, and we put it back here. So we see that the dipole moment is actually the magnitude of dipole is present here. So we see that E equals due to dipole ke times p, or magnitude of p, divided by y square plus a square whole to the power 3/2. So if we just uh, determine the electric field due to a dipole, and now if you see in this slide, we have to find this electric field due to a dipole at a distance y that is uh, much greater than this half distance a. So what we do here, we just see the final formula, this one or this one, and see what will happen if we put y much greater than a. So normally this is the situation. So what you do, you take something common out of that thing. So I just write it separately. E equals ke times P divided by y squared over a squared, y squared plus a squared raised to the power 3 half. And what we do here, so we are considering the case for which y is far away from the dipole. So what this translates to, the point P is far away from the dipole. So the point P that is in the graph, not this P, this is dipole moment, the capital P point that at which we are determining this electric field. So what we do, we take y common out of this fraction. So we have E equals KE times P, and if we take common, so we are getting, actually we are getting y cubed out, not y square or not y3. So what we get out, we get y cubed out, and we are left with 1 plus a square over y square raised to the power 3 half. And if y is much greater than a, then a square over y square approaches 0 when y is much greater than a. So this thing inside the fraction we can ignore. We can ignore this fraction, and we are left with the electric field being equal to KE times Q divided by just a y cube. Sorry, not Q, but a P. KE times P divided by y cube. So this is actually the electric field due to a dipole when the point P at which we are determining the electric field is far away. So you should keep in mind that electric field normally due to a point charge, so there is a difference, you should now pay attention. So there is a different situation than anything else. So for a normal point charge Q, we have an electric field that is proportional to, or that varies with the distance 1 over distance squared that we have studied in our previous lecture. But this is for this electric field was for a point charge. But for a dipole, the dependence of electric field is different, and it varies with 1 over r cubed. So what that means is that electric field due to a dipole, decays faster or faster as one moves away from that. As one moves away from it. So that is the difference. And now you have a slight bit of assignment in the same connection. What you have to do is you have to plot assignment. So you have to plot the electric fields using these two formulas. Plot the electric fields for a point charge and for a dipole as a function of distance. and you can submit these graphs like you submitted for the assignment by your CR. Just one assignment I need to see. I don't need to see everything from each of you. Just one graph will be sufficient from the whole class, but I need to see what you draw. And preferably you draw this graph on some computer program if you have Origin, or if you have Excel, or whatever graphing program you use. So please use that and draw these as a function of distance. You draw these graphs and send it to me via your CR. Okay, so this was the case of an electric dipole. Now we see that if we have a distribution of charges, not point charge but a distribution of charge, so that can be the case when we have a large collection of charges, and you see this volume here, a lump of charge we have here, and we want to determine electric field at some point P, which is at a distance r from that whole charge distribution. So what we do here, we use some other techniques, and although the functional form of the electric field remains the same, it remains exactly the same. So but we have to devise some techniques to calculate electric field, because we do not exactly know how much charge is this. And the other thing is that this lump of charge has no specific shape, it is of an arbitrary shape. So we cannot say that we don't see that this distance is same for all everywhere. So the distance also changes. For charge here, the distance will be different. For the charges at this location, there would be a different distance. So if we are considering a charge at this place here, then this distance would be different. If we are considering here, then it would be different, and if we are here, then it will also be different. So we cannot use exactly one formula that E equals K times Q over R squared. So we have to devise some methods to calculate electric field for this kind of situation. So the what we do here, first thing that we do, we divide this charge whole this complete charge into some volume charge elements or surface charge elements. It depends if we have a volume of charge or a surface of charge. So what we do, we divide charges in equal volume elements or equal area elements. So for example, in this case here, you see we have divided because this is a three-dimensional object. So we have divided the shape into volume charge elements delta Q. You see here, but the condition is that all delta Q's should be of the same magnitude, should be equal, then it would be easy. Should be equal, and then we can determine electric field due to each delta Q present in this. There can be thousands of delta Q in this lump of charge, and we calculate electric field due to each delta Q at point P, and then we add them up. What we do, we determine electric field due to any one of these charges here, and we later what we do, we add the contributions. So we use this summation sign here, as you see, and we just add them up. So for example, we have 10,000 delta Q. So this expression here shows that we are adding the electric fields of all those contributions. And the interesting thing to see here is that we have summation not only over Qi but also over this Ri. This Ri is the distance of each of these elements, and this Ri is also different. So okay, I said that delta Q should be equal, but they can also be different. But if they are equal, that is good. But Ri will never be equal, so R's will be different for each of these components. So we just sum the contributions of electric field and also some the unit vectors, because it's a vector field, so uh, we have to sum the contributions, sum the unit vectors also. And if now we go back to our mathematics that you know from your mathematical courses related to integration, that if we have a large number of things, and we can impose a limit that the things are very very small, if you see here. So now we are imposing the limit that delta q is very small. For to say something is small in mathematics, we say that limit delta qi approaches 0. So then this summation can be converted to integration. That is the case of integration now. And then when we use integration, what we achieve is that the calculations become very easy. So to integrate something is very easy, instead of adding all of them up. So what we do, we convert summation to integration. And normally what we do in our physics course or all the other physics courses, when we have this kind of situation, that we have E equals some constant times integration over charge dq r square r unit vector. So our first task is to determine what is this dq is, what we have written here. So first we determine for each situation. So for each situation, if we can determine dq, then the calculations even become even more convenient or easier. So first step is, in the first step we determine the dq according to the situation. So during the next classes, we do some examples, and we see how determining this dq helps us solving the problem much more easily. So we cannot solve directly just integrating dq. We have to see the situation, and then we have to modify and adopt and adapt. So that would be the case for our next lectures. I just briefly give you a summary of how would we determine that dq. For example, if we have a volume charge density, volume charge like this that we have seen here. So if we have a volume distribution, we will use volume charge density, and volume charge density we will designate with rho, and that would be equal to charge divided by the volume of that element. Second situation can be that we have some charge on some surface area, and for that case we will use this sigma sign, and that we will be the surface charge density, and that would be a charge density that would be obtained by dividing charge with area. And third would be a linear charge density, that we have a charge in some sort of a line like this, and then we have a linear charge density, and for linear charge density we will be using the terminology of lambda, and lambda would be charge divided by the length of that particular case or whatever. And if we have when we are clear with these concepts, then we can determine dq pretty easily. So for volume charge density, dq will be charge density multiplied with the volume element. For surface charge density, that would be equal to surface charge sigma multiplied with dA. And similarly for linear charge, we will have dq equal to lambda dl. And if we can determine that, then it would be pretty easy for us to plug these dq values inside this equation for electric field, and then integrate it, and then we will get the electric field due to that particular charge distribution. So that was it for today's lecture. We will do these examples for different charge distributions in the upcoming week. So you should read these examples from the book also, and we meet during the class session and discuss about